So now we're going to talk about moment of inertia. So moment of inertia is equal to mr squared for anything that's like a point object that's going around something. So all of your mass is a certain distance away from wherever it's orbiting around. And I like to think of moment of inertia as how hard it is to make something rotate. So we're going to start by taking a look at exactly that. So I want you to start by finding a pen or pencil that you might have. And I want you to just rotate it at first. Feel how hard it is to rotate it. It should feel fairly easy to rotate. So I'm just rotating it back and forth. And I could even rotate it back and forth and back and forth and back and forth, and it's still very easy to do. Then I want you to take the same pen and I want you to rotate it like this. Okay. And I want you to pay attention to how much force you're applying or how much torque you're applying to make it rotate. Okay, so remembering that moment of inertia is going to be how hard it is to make this thing rotate. Okay. Then you're going to take the same pen, you're going to hold on to the end of it. And now I want you to rotate it this way. Now, if that moment of inertia is how hard it is to make something rotate, which one was the hardest to make it rotate? The one where you had it like this and rolling it, the one you had it like this, or the one where you held it at the end? So I would say the one that was at the end was the hardest to rotate. And therefore, the bigger the moment of inertia, the harder it is to rotate. So the one that you hold it at the end like this is going to have the biggest moment of inertia. So now we're going to practice calculating the moment of inertia. So if I have an object going around, so in this case, I have a 3 kilogram ball representing the Earth is going around in a circle. The radius of orbit is 1.2 meters, and I want to know what is the moment of inertia of the Earth model. Pause this. I want you to try it and then resume. All right. So the way you do this is you are going to use your equation I equals mr squared. And the mass is 3, and your radius is 1.2. Don't forget to square it because your radius is squared, and you get 4.32. So one question I often get is, what are the units for moment of inertia? Well, the easiest way to do that is to look at the equation for moment of inertia and go from there. So in this case, I have moment of inertia is equal to mr squared. Well, mass, the units are kilograms, and radius, the units are meters. So when I square that radius, I'm going to square my meters. Therefore, my units for moment of inertia are kilograms times meters squared. So pretty straightforward. So next we have two 3 kilogram balls, and they're going around in a circle. The radius of the orbit is 1.2 meters, and I want to know what is the moment of inertia of the two balls together. So there's a couple different ways to do this. Go ahead and pause. I want you to do it and then resume. So the first way that I want to show you to find your moment of inertia is by using the total mass of the system. This is the most common that students will do. They will do the total mass times the distance that the mass is from the center. So your radius in this case, squared. So because you have two 3 kilogram masses, you're going to have a total mass of 6 kilograms, and then you'll use your 1.2 meters to get a total moment of inertia of 8.64. The other way to do this is you can find the moment of inertia of each one and add them together to get the total moment of inertia. So I know from the previous one that both of the balls will individually be 4.32, and I can add those together to get 8.64. So either way you do it, you get the same answer. Now, the first way that you do it is this mass way. If you think of the total mass, well, then I could also think of this as having lots and lots and lots of little balls. And if I add up lots and lots and lots of balls, all of small amounts of mass, and I find the total mass of the whole thing, then, and they're all a distance of r from the center, then I could also say that it would be the moment of inertia would be equal to the mass of the whole thing times the radius of the whole thing. So this is kind of taking that and just going to the extreme with it. So this is called a hoop. A hoop has the same moment of inertia as a ball on a stick. This is going to be one of the moments of inertia that you should memorize and write down. So both for when you just had a point going around, it was mr squared. Now we have a hoop is also mr squared. But that doesn't work so well when you have balls that are at different places. So I have two 3-kilogram balls. They're going around in a circle. The radius of the orbit of one of them is 1.2 meters, and the radius of the other is 0.7 meters. And I want to know what is the moment of inertia of the balls. So this one, we're going to have to use the moment of inertia of one ball, figure out what it is, and add it to the moment of inertia of the other ball to find my total moment of inertia. Go ahead and pause and do that, and then resume. All right, so I put moment of inertia of the first plus the second. So I'm putting in the mass of the first times the radius of the first squared plus mass of the second times radius of the second squared. I can plug in all of those numbers that are given in the problem, and I get 5.79 as my total moment of inertia. Now I want you to do number 39. A playground toy has 4 seats, each of which are 5 kilograms, attached to a very light 1.5 meter long rods as seen from above in that figure. If 2 children with masses of 15 kilograms and 20 kilograms sit in seats opposite one another, what is the moment of inertia about the rotation axis? Go ahead and pause and do it. Now, one thing to pay attention to is that this has 4 seats. If you forgot to do 4 seats, pause, try again. Otherwise, if not, I'm going to proceed. So I have the total moment of inertia is equal to the moment of inertia of the 4 chairs plus one child plus the second child. So I have my moment of inertia is equal to 4 times the moment of inertia of one chair plus I had the moment of inertia of the first child plus the moment of inertia of the second child. And for all of these, I just left it as R because all the seats and kids are all the same distance away. So I did not need to put anything after the R because they're all the same R. Then I plugged in the numbers. So I put all the masses and radii in, and I get a total of 123.75 for my moment of inertia. And that should be kilograms times meters squared. So now that we have learned about finding the moment of inertia of something with multiple parts, I want to look at what it means if we make something into a ton of tiny pieces. So with one thing going around and around, we had one ball going around, and it was mr squared for that dot. When we had 2, then we had these 2 going around, and we just could add the masses together. Then we had a whole bunch of dots, each with a mass, each with a radius right here of whatever this radius in the red bar represents. Well, let's add now another row of dots on the inside of that. Well, that row of dots is going to be closer. So the mass of however much it is going to be closer in towards the center. And then I could do it again and again. If I add up all of these masses times their radii squared, if I add them all up, I get a total of 1/2 times the total mass of this solid cylinder times r squared. Now, if you care about y, take calculus. This is called the integral. And you can learn about it by taking calculus. So it is not something you need to memorize here for the y. All you need to do is accept that that is true. And in fact, there are many other shapes Oops, there we go. And all of these shapes are on page 210 in your textbook. So you do not need to memorize these. Please do not memorize these. The only ones that you do need to memorize are the two that I have just gone over, the cylinder or disc about as it rotates, or a cylindrical hoop about its center. So it makes sense if you think about moment of inertia as being your mass of a part of it times the radius squared, that as you have more mass farther away from where it's rotating, so if I had this rotating like this around, that this part, like all the mass is far away from the center. None of the mass is in here and close. So this is going to have a much bigger moment of inertia because all the mass is at a bigger distance or radius from that center of rotation as this rolls. Now, if I have something solid, and I have this rotating, you'll notice that some of this mass that's close to the center is not going around as far. So here's the middle. I'm going to draw the middle here. So if I have this little dot that represents the mass, this middle, this is the center here. I'll draw it like a bullseye. And this little piece of mass, as I rotate it, it doesn't go very far away from the center of mass compared to a dot out here on the edge. As I rotate that, it goes much farther away from the center. And therefore, this part of it is going to have a much bigger moment of inertia. But because some of the mass of this thing is close in comparison to this one, where all the mass is far away, this is going to end up having a smaller moment of inertia because you have some of the mass close by. So if both of these have the same mass, this one, it will have the smaller moment of inertia. So what you need to know about this is you do not need to memorize all these moments of inertia. You will always be given this, or when you're doing your homework, you will have access to your book and you will be expected to look up these numbers, not have them memorized. The only two you need to know is a cylinder and a cylindrical hoop, or sorry, cylinder, solid cylinder, or a cylindrical hoop. So these are the only two that you need to know. 1/2 mr squared and mr squared. Then the other thing you need to be able to do is to be able to tell me which one has a bigger moment of inertia. So if right now I look at these two just to compare them, this is like when you had your pen and the first or the second one that I had you do is you went like this. Well, as I'm looking at this, the biggest distance that my mass has away from the center of where I'm rotating it is only this far on either side. If instead I hold it like this, now the biggest distance I have is much bigger. And in fact, before it was only this much. So all of this is all going to have a bigger radius, which means that this I expect when I go like this to have a much bigger moment of inertia and that it's going to be harder for it to twist. So if you look here, I have 1/3 ml squared versus 1/12 ml squared. So this one is 4 times bigger than that one. And it makes sense. Now, what I want you to do is find a piece of paper and crumple it up in a ball, or find a ball or a stuffed animal. In my case, I have the dog donated dog toy that I have attempted to smash together into a little ball and attach it to itself with a rubber band because it was the shape of a frisbee. So we've got dog toy helper ladybug thing. And as I rotate this ball, for lack of a better word, you will notice that where I'm holding it on the edges here is not going to move very far away from my hand. So if I go like this, you can see that right here, it's not going very far away. So my radius to this part of the mass is fairly small. The part where it does have a big mass is where the head of my ladybug is, because that's the fat part of this wad. And as I have it rotate this way, you can also see that it's going farther away from where I'm rotating it. So if I take and draw, oh, I can't draw in the picture. Well, you can see here, if this is where I'm rotating it, like this, the head of it is quite a bit farther away than where my hands are. And what matters is that radius. Now, if I'm going to compare this solid sphere to a cylinder a cylinder or disc, the difference for this is as I rotate it like this, a cylinder would be solid all the way. So if I have my can of olives here like this, you'll notice that as I rotate it this way, the cylinder stays, like the outside of it stays all the way out to this point, whereas the toy or a ball gets narrow at the edges. So even though these might have the same radius, what matters here is that these edges on the ball get smaller as you get closer to where I'm rotating it around. It gets narrower here, whereas on a cylinder it doesn't. And so I end up having more mass farther away from where I'm rotating it for this solid cylinder than I do for the ball. Now I want to be able to compare something that is a solid sphere like a bowling ball and compare that to something like a tennis ball or a ping pong ball where the center of it is hollow. So thinking again, just like how we compared the solid cylinder to a cylindrical hoop, the spherical shell or a ping pong ball or tennis ball where the middle is empty doesn't have any mass in the middle, which means that there's no mass that can be close to that rotational axis. But the solid one does have mass that can be close to that center of rotation, which means that the spherical shell is going to end up having a bigger moment of inertia because more mass is farther away from where you're rotating it. So it makes sense that this is 2/3 mr squared and this is 2/5 mr squared. So what we're going to do is we are going to have these objects go down the hill. This is the Flippin Physics guy. So a hollow sphere, solid sphere, and thin hoop are simultaneously released from rest at the top of an incline. Which will reach the bottom first? Assume all objects are of uniform density. So the blue ball is a hollow sphere, the yellow one is a solid sphere, and there is a thin hoop. All of them start from rest, so their initial velocity is 0, and all their densities are equal. So you're going to end up having like the same mass. All right. Well, I want you to think about moment of inertia. And I want you to think about hollow sphere, solid sphere, and thin hoop and guess which one's going to end up at the bottom first. Okay, now let's find out. So it looks like the yellow ball makes it to the bottom first, followed by the blue ball, and then the hoop. So let's take a look at this. So that means that our solid sphere made it to the bottom first, followed by our spherical shell or hollow ball, and lastly, our cylindrical hoop. Now, what does this mean? Does it make sense? Most students guess that the thin hoop is going to make it to the bottom first because it has a bigger moment of inertia. But if you remembered at the beginning of this lecture today, we talked about how moment of inertia, the bigger it is, the harder it is to get it to roll. Well, you have a bigger moment of inertia. That means it's going to be harder to get that one to roll, which in this case is going to be the thin hoop. So bigger moment of inertia means we're going to expect a smaller angular acceleration. Likewise, the one with the smallest moment of inertia, or our solid sphere, then we expect to end up at the bottom first.